The time will come when diligent research over long periods will bring to light things which now lie hidden. A single lifetime, even though entirely devoted to the sky, would not be enough for the investigation of so vast a subject. And so this knowledge will be unfolded only through long successive ages. There will come a time when our descendants will be amazed that we did not know things that are so plain to them. Many discoveries are reserved for ages still to come, when memory of us will have been effaced. Our universe is a sorry little affair unless it has in it something for every age to investigate. Nature does not reveal her mysteries once and for all. Seneca, Natural Questions, Book 7. The cosmos is all that is, or ever was, or ever will be. Our feeblest contemplations of the cosmos stir us. There is a tingling in the spine, a catch in the voice, a faint sensation, as if a distant memory are falling from a height. We know we are approaching the greatest of mysteries. The size and age of the cosmos are beyond ordinary human understanding. Lost somewhere between immensity and eternity is our tiny planetary home. In a cosmic perspective, most human concerns seem insignificant, even petty. And yet our species is young and curious and brave and shows much promise. In the last few millennia, we have made the most astonishing and unexpected discoveries about the cosmos and our place within it, explorations that are exhilarating to consider. They remind us that humans have evolved to wonder, that understanding is a joy, that knowledge is prerequisite to survival. I believe our future depends on how well we know this cosmos in which we float like a mote of dust in the morning sky. Those explorations required skepticism and imagination both. Imagination will often carry us to worlds that never were, but without it, we go nowhere. Skepticism enables us to distinguish fancy from fact, to test our speculations. The cosmos is rich beyond measure in elegant facts, in exquisite interrelationships, in the subtle machinery of awe. The surface of the earth is the shore of the cosmic ocean. From it, we have learned most of what we know. Recently, we have waded a little out to sea, enough to dampen our toes or, at most, wet our ankles. The water seems inviting. The ocean calls. Some part of our being knows this is from where we came. We long to return. These aspirations are not, I think, irreverent, although they may trouble whatever gods may be. The dimensions of the cosmos are so large that using familiar units of distance, such as meters or miles, chosen for their utility on Earth, would make little sense. Instead, we measure distance with the speed of light. In 1 second, a beam of light travels 186,000 miles, nearly 300,000 kilometers or 7 times around the Earth. In 8 minutes, it will travel from the sun to the Earth. We can say the sun is 8 light minutes away. In a year, it crosses nearly 10 trillion kilometers, about 6 trillion miles of intervening space. That unit of length, the distance light goes in a year, is called a light year. It measures not time but distances, enormous distances. The Earth is a place. It is by no means the only place. It is not even a typical place. No planet or star or galaxy can be typical because the cosmos is mostly empty. The only typical place is within the vast, cold, universal vacuum, the everlasting night of intergalactic space, a place so strange and desolate that, by comparison, planets and stars and galaxies seem achingly rare and lovely. If we were randomly inserted into the cosmos, the chance that we would find ourselves on or near a planet would be less than 1 in a billion trillion trillion, 10 to the 33rd power. In everyday life, such odds are called compelling. Worlds are precious. From an intergalactic vantage point, we would see, strewn like sea froth on the waves of space, innumerable faint, wispy tendrils of light. These are the galaxies. Some are solitary wanderers. Most inhabit communal clusters, huddling together, drifting endlessly in the great cosmic dark. Before us is the cosmos on the grandest scale we know. We are in the realm of the nebulae, 8 billion light years from Earth, halfway to the edge of the known universe. A galaxy is composed of gas and dust and stars, billions upon billions of stars. Every star may be a sun to someone. Within a galaxy are stars and worlds, and, it may be, a proliferation of living things and intelligent beings and spacefaring civilizations. But from afar, a galaxy reminds me more of a collection of lovely found objects, seashells perhaps, or corals, the productions of nature laboring for eons in the cosmic ocean. There are some 100 billion, 10 to the 11th, galaxies, each with, on the average, 100 billion stars. In all the galaxies, there are perhaps as many planets as stars. 10 to the 11th times 10 to the 11th, 10 to the 22nd power, 10 billion trillion. In the face of such overpowering numbers, what is the likelihood that only one ordinary star, the sun, is accompanied by an inhabited planet? Why should we, tucked away in some forgotten corner of the cosmos, be so fortunate? To me, it seems far more likely that the universe is brimming over with life. But we humans do not yet know. We are just beginning our explorations. From 8 billion light years away, we are hard pressed to find even the cluster in which our Milky Way galaxy is embedded, much less the sun or the Earth. The only planet we are sure is inhabited is a tiny speck of rock and metal, shining feebly by reflected sunlight, and at this distance, utterly lost. But presently our journey takes us to what astronomers on Earth like to call the local group of galaxies. Several million light years across, it is composed of some 20 constituent galaxies. It is a sparse and obscure and unpretentious cluster. One of these galaxies is M31, seen from the Earth in the constellation Andromeda. Like other spiral galaxies, it is a huge pinwheel of stars, gas, and dust. M31 has two small satellites, dwarf elliptical galaxies bound to it by gravity, by the identical law of physics that tends to keep me in my chair. The laws of nature are the same throughout the cosmos. We are now 2 million light years from home. Beyond M31 is another very similar galaxy, our own, its spiral arms turning slowly every quarter billion years. Now, 40,000 light years from home, we find ourselves falling toward the massive center of the Milky Way. But if we wish to find the Earth, we must redirect our course to the remote outskirts of the galaxy, to an obscure locale near the edge of a distant spiral arm. Our overwhelming impression, even between the spiral arms, is of stars streaming by us, a vast array of exquisitely self-luminous stars, some as flimsy as a soap bubble and so large that they could contain 10,000 suns or a trillion Earths. Others the size of a small town and 100 trillion times denser than lead. Some stars are solitary like the sun. Most have companions. Systems are commonly double, two stars orbiting one another. But there is a continuous gradation from triple systems through loose clusters of a few dozen stars to the great globular clusters, resplendent with a million suns. Cosmos by Carl Sagan. When on board HMS Beagle, as naturalist, I was much struck with certain facts in the distribution of the inhabitants of South America, and in the geological relations of the present to the past inhabitants of that continent. These facts seem to me to throw some light on the origin of species, that mystery of mysteries, as it has been called by one of our greatest philosophers. On my return home, it occurred to me in 1837 that something might perhaps be made out on this question by patiently accumulating and reflecting on all sorts of facts which could possibly have any bearing on it. These I enlarged in 1844 into a sketch of the conclusions, which then seemed to me probable. From that period to the present day, I have steadily pursued the same object. I hope that I may be excused for entering on these personal details, as I give them to show that I have not been hasty in coming to a decision. My work is now nearly finished, but as it will take me 2 or 3 more years to complete it, and as my health is far from strong, I have been urged to publish this abstract. I have more especially been induced to do this as Mr. Wallace, who is now studying the natural history of the Malay archipelago, has arrived at almost exactly the same general conclusions that I have on the origin of species. Last year, he sent to me a memoir on this subject, with a request that I would forward it to Sir Charles Lyell, who sent it to the Linnean Society, and it is published in the third volume of the Journal of that society. Sir C. Lyell and Dr. Hooker, who both knew of my work, the latter having read my sketch of 1844, honored me by thinking it advisable to publish, with Mr. Wallace's excellent memoir, some brief extracts from my manuscripts. The abstract, which I now publish, must necessarily be imperfect. I cannot here give references and authorities for my several statements, and I must trust to the reader reposing some confidence in my accuracy. No doubt errors will have crept in, though I hope I have always been cautious and trusting to good authorities alone. I can here give only the general conclusions at which I have arrived, with a few facts and illustration, but which I hope in most cases will suffice. No one can feel more sensible than I do of the necessity of hereafter publishing in detail all the facts, with references, on which my conclusions have been grounded, and I hope in a future work to do this. For I am well aware that scarcely a single point is discussed in this volume on which facts cannot be adduced, often apparently leading to conclusions directly opposite to those at which I have arrived. A fair result can be obtained only by fully stating and balancing the facts and arguments on both sides of each question, and this cannot possibly be done here. I much regret that want of space prevents my having the satisfaction of acknowledging the generous assistance which I have received from very many naturalists, some of them personally unknown to me. I cannot, however, let this opportunity pass without expressing my deep obligations to Dr. Hooker, who for the last 15 years has aided me in every possible way by his large stores of knowledge and his excellent judgment. In considering the origin of species, it is quite conceivable that a naturalist, reflecting on the mutual affinities of organic beings, on their embryological relations, their geographical distribution, geological succession, and other such facts, might come to the conclusion that each species had not been independently created, but had descended, like varieties, from other species. Nevertheless, such a conclusion, even if well founded, would be unsatisfactory until it could be shown how the innumerable species inhabiting this world have been modified so as to acquire that perfection of structure and coadaptation which most justly excites our admiration. Naturalists continually refer to external conditions, such as climate, food, etc., as the only possible cause of variation. In one very limited sense, as we shall hereafter see, this may be true, but it is preposterous to attribute to mere external conditions the structure, for instance, of the woodpecker, with its feet, tail, beak, and tongue, so admirably adapted to catch insects under the bark of trees. In the case of the mistletoe, which draws its nourishment from certain trees, which has seeds that must be transported by certain birds, and which has flowers with separate sexes absolutely requiring the agency of certain insects to bring pollen from one flower to the other, it is equally preposterous to account for the structure of this parasite, with its relations to several distinct organic beings, by the effects of external conditions, or of habit, or of the volition of the plant itself. The author of The Vestiges of Creation would, I presume, say that after a certain unknown number of generations, some bird had given birth to a woodpecker, and some plant to the mistletoe, and that these had been produced perfect as we now see them. But this assumption seems to me to be no explanation, for it leaves the case of the coadaptations of organic beings to each other and to their physical conditions of life untouched and unexplained. It is therefore of the highest importance to gain a clear insight into the means of modification and coadaptation. At the commencement of my observations, it seemed to me probable that a careful study of domesticated animals and of cultivated plants would offer the best chance of making out this obscure problem. Nor have I been disappointed. In this, and in all other perplexing cases, I have invariably found that our knowledge, imperfect though it may be, of variation under domestication, afforded the best and safest clue. I may venture to express my conviction of the high value of such studies, although they have been very commonly neglected by naturalists. From these considerations, I shall devote the first chapter of this abstract to variation under domestication. We shall thus see that a large amount of hereditary modification is at least possible, and what is equally or more important, we shall see how great is the power of man in accumulating by his selection successive slight variations. I will then pass on to the variability of species in a state of nature, but I shall unfortunately be compelled to treat this subject far too briefly, as it can be treated properly only by giving long catalogues of facts. We shall, however, be enabled to discuss what circumstances are most favorable to variation. In the next chapter, the struggle for existence amongst all organic beings throughout the world, which inevitably follows from their high geometrical powers of increase, will be treated of. This is the doctrine of Malthus, applied to the whole animal and vegetable kingdoms. As many more individuals of each species are born than can possibly survive, and as, consequently, there is a frequently recurring struggle for existence, it follows that any being, if it vary however slightly in any manner profitable to itself, under the complex and sometimes varying conditions of life, will have a better chance of surviving, and thus be naturally selected. From the strong principle of inheritance, any selected variety will tend to propagate its new and modified form. This fundamental subject of natural selection will be treated at some length in the fourth chapter, and we shall then see how natural selection almost inevitably causes much extinction of the less improved forms of life and induces what I have called divergence of character. In the next chapter, I shall discuss the complex and little-known laws of variation and of correlation of growth. In the four succeeding chapters, the most apparent and greatest difficulties on the theory will be given. Namely, first, the difficulties of transitions, or an understanding how a simple being or a simple organ can be changed and perfected into a highly developed being or elaborately constructed organ. Secondly, the subject of instinct, or the mental powers of animals. Thirdly, hybridism, or the infertility of species and the fertility of varieties when intercrossed. And fourthly, the imperfection of the geological record. In the next chapter, I shall consider the geological succession of organic beings throughout time. In the 11th and 12th, their geographical distribution throughout space. In the 13th, their classification or mutual affinities, both when mature and in an embryonic condition. In the last chapter, I shall give a brief recapitulation of the whole work and a few concluding remarks. No one ought to feel surprised at much remaining as yet unexplained in regard to the origin of species and varieties, if he makes due allowance for our profound ignorance in regard to the mutual relations of all the beings which live around us. Who can explain why one species ranges widely and is very numerous, and why another allied species has a narrow range and is rare? Yet these relations are of the highest importance, for they determine the present welfare and, as I believe, the future success and modification of every inhabitant of this world. Still less do we know of the mutual relations of the innumerable inhabitants of the world during the many past geological epochs in its history. Although much remains obscure, and will long remain obscure, I can entertain no doubt, after the most deliberate study and dispassionate judgment of which I am capable, that the view which most naturalists entertain, and which I formerly entertained, namely, that each species has been independently created, is erroneous. I am fully convinced that species are not immutable, but that those belonging to what are called the same genera are lineal descendants of some other and generally extinct species, in the same manner as the acknowledged varieties of any one species are the descendants of that species. Furthermore, I am convinced that natural selection has been the main, but not exclusive means of modification. Introduction on the Origin of Species by Charles Darwin.